Welcome. In this video, we will explore the critical process of maintaining and evolving machine learning, or ML, systems once they are deployed into the real world. This process, often referred to as MLOps, is what keeps intelligent applications accurate and reliable over time. Let's get started. When we talk about maintaining and evolving ML systems, we are referring to the entire lifecycle of an ML project, which is highly iterative. Unlike traditional software development, where a product might be considered done once it meets requirements, ML systems are constantly cycling through different stages. The core phases include planning the project, preparing the data, actually building and training the model, deploying the system so users can access it, monitoring how it performs in the real world, and then continually learning and updating the model based on new information. This continuous loop is essential because ML models depend heavily on data. Since the real world changes constantly, the data changes too. Therefore, the models must also change and adapt to remain useful. We need to ensure the system meets crucial requirements like reliability, meaning it always works, and adaptability, meaning it can change easily as new data or needs arise. This entire process, often called MLOps, ensures that the model remains accurate and valuable over time. What have we learned about the ML system lifecycle? It is a continuous loop of building, deploying, monitoring, and updating, driven by the changing nature of real-world data. This flowchart illustrates the iterative process of developing and maintaining an ML system. We start at the top with project scoping, which defines the initial goals. This leads directly to data engineering, where the necessary data is prepared and cleaned. Once data is ready, we move to the model development phase, which is where the algorithms are trained and evaluated offline. A successful model then proceeds to deployment, where it is made accessible to users in a production environment. Once deployed, the system enters the crucial stage of monitoring and continual learning, constantly checking performance and gathering new data. This monitoring phase feeds back into business analysis, determining if the system is still meeting organizational objectives. If not, the process loops back to project scoping, or directly back to data engineering if more data is needed, or the existing data pipeline requires adjustment. This cycling structure emphasizes that maintenance and evolution are continuous and planned activities within the lifecycle, not just afterthoughts. The biggest differentiator between an ML system in development and an ML system in production is the data. In school or during the initial development phase, we often work with clean, pre-packaged, unchanging datasets. This allows us to focus purely on the algorithm. However, in the real world, production data is almost always messy and noisy. Crucially, it is not static. It is constantly shifting and changing over time. This dynamic nature means that the original model, trained on old, static data, will eventually become outdated. If we treat the production data as if it were stationary, meaning unchanging, our model will perform poorly over time. This makes the effort spent on gathering new or improved data, known as data iteration, potentially much more valuable for system performance than advanced algorithmic tuning. We must accept that maintaining the data quality and relevance is the primary challenge in long-term ML system maintenance. What have we learned about data in production? Production data is constantly changing and messy, making the initial assumption that data is static fundamentally wrong. This diagram contrasts the characteristics of data typically encountered in a research or academic setting, with data found in a real-world production environment. In academia, data is often static, meaning it does not change, and is clean and perfectly formatted, allowing researchers to concentrate solely on algorithm optimization. However, once an ML system is deployed, the data it encounters is constantly shifting and changing, making the environment dynamic. Furthermore, production data tends to be messy, noisy, and inherently biased, presenting significant engineering challenges that overshadow simple algorithmic performance. The real-world focus shifts towards building models that are adaptable and reliable enough to handle these continuous, unpredictable changes in the input data streams. This fundamental difference underscores why managing data effectively is central to maintaining and evolving production ML systems. Since production data is always changing, we need to know how these changes manifest. The general term for the discrepancy between the expected data and the data actually seen is a data distribution shift. One major consequence of this shift is called train-serving skew. This happens when your model works perfectly during testing because it was trained on historical data but then fails miserably in the real world, or when serving, because the real-world inputs are slightly different in structure or format from the training data. There are two main types of natural data shifts. The first is concept drift, where the underlying relationship itself changes. For example, if a model predicts house prices, and suddenly a new policy is passed that changes how location affects price, the old concept drifts, making the model inaccurate. The second type is covariate shift, where the input data itself changes, but the underlying rule stays the same. For instance, If your spam filter suddenly sees emails using new kinds of popular slang, that is a covariate shift. What have we learned about data shifts? We learned that train-serving skew is when training data differs from real-world data, and shifts like concept drift change the rules, while covariate shift changes the inputs. Operational metrics only tell us if the lights are on. We need to monitor operational health to make sure the system meets its expected performance metrics, such as how fast it runs and how reliable it is. This is similar to monitoring any traditional software application. We track metrics like latency, which is the time it takes for the system to return a prediction. If the latency is too high, the system might be useless, especially for real-time applications like autocompletion. We also track throughput, which measures the volume of requests the system handles per minute or hour. Additionally, monitoring hardware usage, like CPU or GPU utilization, ensures the system is running efficiently and predictably. If the system fails to meet these operational expectations, it fails, regardless of how accurate the ML model inside might be. Therefore, simplicity in design is vital, as overly complex systems increase the risk of failures related to reliability and runtime, making maintenance extremely challenging. What have we learned about operational monitoring? We learned that ML systems must track operational metrics like latency and throughput to ensure the software is reliable and fast, because a down system is useless, no matter how smart the model is. This diagram visualizes the 3 general layers of operational monitoring required for maintaining system health in a production environment. System health is broken down into 3 fundamental layers: the network layer, the machine layer, and the application layer. Monitoring the network layer helps detect issues related to data transfer speed, usually quantified by latency. The machine layer monitoring focuses on the physical or virtual hardware resources, tracking essential metrics like CPU, GPU utilization to ensure efficient resource allocation. Finally, the application layer focuses on the performance of the running service itself, tracking metrics such as overall throughput, which is the request volume, and error codes, ensuring successful prediction requests. Together, these layers provide a comprehensive view of the system's operational reliability. Operational metrics only tell us if the lights are on. Model-specific metrics tell us if the predictions are actually useful, preventing the model from running and producing garbage silently. We monitor 4 key artifacts, moving from the end of the pipeline back to the start. The easiest artifact to monitor is accuracy, but this requires natural labels, meaning automatic feedback from user actions, like a user clicking on a recommended item. If accuracy isn't available immediately due to delayed feedback, we monitor the predictions themselves, checking if the output distribution changes significantly, like suddenly recommending only one type of product. Moving further upstream, we monitor the extracted features, and finally the raw inputs. While monitoring raw inputs is the hardest task because the data is usually unstructured and messy, it provides the earliest warning of potential data distribution shifts, such as new types of inputs appearing. This complete view ensures that the model remains scientifically sound, not just functionally sound. What have we learned about model monitoring? Model monitoring involves checking accuracy, predictions, features, and raw inputs to detect changes in the data or model behavior, especially prioritizing raw inputs for early warnings about shifts. This diagram shows the pipeline of model health monitoring and highlights the relative difficulty of tracking different metrics. The pipeline progresses from raw inputs through feature extraction, leading to the final predictions, and finally to accuracy, if ground truth labels are available. Monitoring raw inputs is generally the hardest task because inputs are often messy and unstructured, but it provides the earliest indication of data shifts. As data flows through the pipeline, it becomes more structured and easier to monitor, moving towards features, then predictions, and finally accuracy. A change detected late in the pipeline, such as a drop in accuracy, requires immediate investigation upstream to determine whether the problem lies with the data, the features, or the model itself. When monitoring reveals that a model's performance is degrading due to changes in the real world, the solution is continual learning. This refers to the practice of actively updating your ML models using new data to adapt to distribution shifts. Instead of waiting for a complete model failure or a predefined long interval, models are updated frequently. For many companies, this starts by moving from manual ad hoc updates, which are time-consuming and unreliable, to automated retraining. Automated retraining involves creating scripts and workflows to pull new data, extract features, and retrain the model on a schedule, often using batch processes. If we are using complex models like neural networks, we must be careful not to update the model with every single data point, as this can cause catastrophic forgetting, where the network abruptly forgets old, previously learned information. Instead, updates are performed in microbatches, small, optimized groups of data points, ensuring stability and performance. What have we learned about continual learning? It is the practice of frequently updating models, often automatically, to counter data shifts, and microbatches are used for complex models like neural networks to avoid forgetting old information. This diagram maps the automated retraining loops central to continual learning. The process begins with continuous monitoring, which detects performance degradation, and triggers retraining using a scheduler. This automated step then proceeds to pull new data, which is constantly streaming in from the production environments. The next phase is to extract features and process labels from this new data, ensuring consistency with the original training pipeline. The core step is to train the model, often using microbatches to update the existing model state effectively. A decision point checks if the new model is ready, which involves assessing metrics. If successful, it proceeds to the evaluation and deployment pipeline before returning to continuous monitoring, restarting the adaptation cycle. When we have a newly retrained model, we cannot simply replace the old one, as this could lead to catastrophic failures if the new model is flawed or unstable. To ensure safety and reliability, we use the champion/challenger strategy. The existing model, which is currently serving predictions to users, is known as the champion model. The newly trained or updated model is referred to as the challenger. The challenger is deployed alongside the champion, but is exposed only to a small fraction of the live user traffic, allowing us to test its performance in a real production environment. This comparative testing is often done via A/B testing. If the challenger consistently demonstrates better performance, lower errors, and higher reliability than the champion, it is promoted and replaces the champion. If it performs worse, it is discarded, and the reliable champion remains in place. This strategy is key to implementing continual learning safely and minimizing any potential harm to users or the business from bad updates. What have we learned about safe deployment? We learned that the champion is the current model, the challenger is the new model, and we use live testing or A/B testing to compare them safely before promoting the challenger. This diagram shows how the champion/challenger deployment pattern works using a traffic split. Incoming live traffic is directed to a traffic split module, typically performing an A/B test. The majority of traffic, often around 95%, is routed to the stable champion model, denoted as version 1.0. A smaller percentage of traffic goes to the new challenger model, v1.1, for testing. Both models' performances are recorded in the monitor performance stage. A crucial decision point checks if the challenger outperforms the champion based on defined metrics. If yes, the challenger is promoted to the new champion and begins receiving all traffic. If no, the challenger is discarded, and the champion continues operating. This parallel testing minimizes risk, while ensuring that only proven improvements are pushed into the production environment. The final lesson in maintaining and evolving ML systems is the paramount importance of simplicity and engineering robustness. For a model to be easily maintainable and highly adaptable, it must be built on a simple, predictable, and reliable foundation. Overcomplicating systems adds technical debt, increasing the likelihood of failure in areas like reliability, runtime, and memory usage. Every component, from the data pipeline to the deployment mechanism, should be scrutinized to ensure its benefit outweighs the complexity it introduces. Maintainability is crucial because ML projects involve many stakeholders: data scientists, software engineers, and domain experts, who need to easily collaborate and understand the system logic. Ultimately, long-term evolution and rapid iteration, especially the shift toward automated continual learning, hinges entirely on having the right infrastructural support, tooling, and ML platforms that standardize and simplify the development workflow for everyone involved. What have we learned about maintenance fundamentals? We learned that simplicity, robustness, and the proper infrastructure are essential for maintainability, ensuring that ML systems are predictable and easy for multiple teams to collaborate on over time. This mind map summarizes the key requirements necessary for any ML system, intended for long-term maintenance and evolution. The first goal is maintainability, ensuring the system logic is clear and facilitates collaboration among different experts, such as engineers and subject matter experts. Second is adaptability, the system's ability to cope with data distribution shifts through rapid updates and continual learning cycles. These factors rely on core robustness and reliability, emphasizing that simplicity is the key defense against high technical debt and unpredictability. Finally, all these requirements depend heavily on robust infrastructure support, which provides the necessary automated tooling, platforms, and versioning capabilities to manage the complexity inherent in data-driven systems.